Hello, everyone. In the previous video, we saw how we can solve indefinite and definite integrals that involve powers and products of trigonometric functions. In this video today, we're going to continue our exploration of trigonometric integration. But what we're going to focus on is how we can substitute for a trigonometric function in order to simplify what might be a complicated integral. So let me start by illustrating exactly what I mean here. Let's suppose that you were maybe given an integral that involves, say, the square root of a squared plus x squared. Now, I'm not going to write down the exact integral, but imagine you are unable to, say, do a usual substitution, say u is equal to a squared plus x squared. And in this case, a is just any number, right? So don't let that confuse you. X is, again, the variable of integration. So if you're unable to do a regular substitution here, you're sort of up the creek. We don't know what we can possibly do. But what I'm going to propose to you is we're actually going to substitute x for a trigonometric function of a new variable, say theta, and we can take advantage of a lot of trigonometric identities in order to simplify this integral. So for example, if our integrand involves this square root of a squared plus x squared, then what we could do is we could maybe say x is equal to a times tan of theta. So now theta is my new independent variable. And look what happens here. This gives me a squared plus x squared underneath the square root. This will become a squared plus a squared tan squared of theta. And I can factor out an a squared from this. And this leaves me with 1 plus tan squared of theta, which we know from the second Pythagorean trigonometric identity, this is actually equal to a squared secant squared of theta. And so if you look at what's happened here, you have taken the square root of a squared plus x squared, and you've turned it into the square root of two things that are square, a squared and secant squared. Now, of course, we have to be careful when we take these square roots of squares. We have absolute values that pop up, but we'll deal with that in a moment. Let's think about one other issue that could arise here. And that issue is, okay, maybe I can solve my integral in terms of theta now, but one of the big things that I always emphasize with substitution is no one asked me about theta. Everybody was asking me about x. So how do I get back, right? It's not necessarily as simple as back substituting here, but what we can do is we can use the usual trigonometric meanings here, like in terms of right angle triangles. So maybe SOHCAHTOA, if you're familiar with that, in order to solve for theta in terms of the other trigonometric functions which might arise, for example, secant. So let me show you what I mean. Our substitution for x is equal to a tan theta, this is the same as saying that tan of theta is equal to x over a. So if we call this angle down here, say theta, then we know that tan is given by the opposite over adjacent. So that means that if this is a right angle, we have x here running vertically, we have a here running horizontally. And from the Pythagorean theorem, we also know that we have a squared plus x squared running along the hypotenuse here. But now what this allows us to do is this allows us to back substitute for any single trigonometric function as a function of theta in terms of x and say a. And the advantage that this has is that when you perform trigonometric integration, just because we're substituting for tan theta doesn't mean that tan theta is going to come up in the solution all the time. For example, if we did this substitution, we would be left with a secant. And if we integrate secant up, we get, I believe it's the ln of the absolute value of tan plus secant. And both of those are functions of theta. So we have what tan of theta would be, but from this triangle, we can also get what secant of theta will be. For example, secant of theta is equal to 1 over cosine of theta. So we can use SOHCAHTOA, regular trigonometry, to get what cos of theta would be out of this thing. So cos of theta is it is the adjacent over the hypotenuse. So this is a over the square root of a squared plus x squared. And so that tells me that now I have an explicit formula for secant of theta as well, which is x squared plus a squared. The order doesn't matter because we're adding, divided by a, there's no square, sorry. And you can do the same thing. If a sine popped up, then you could find what sine of theta is as well, and you can back substitute. So we can always recover the variables here. And the really cool thing about this is that this can also extend to, say, an integral of the form maybe a squared minus x squared. And in this case, you would substitute x is equal to, say, a sine of theta. And the reason for that is because you will get a squared minus a squared sine theta, which means that this becomes the square root of a squared cos squared of theta, right? So this is just the Pythagorean identity again. And you can do the same thing for maybe if you reverse those negative components. If you have x squared minus a squared, in this case, you could say x is equal to a secant of theta. And in this case, you use that Pythagorean identity again, the one that involves tans and secants. And here you get a square root of a squared tan squared of theta. And so the beauty here is that you get a perfect square underneath the square root. There is a slight issue though, and we have to be careful of when these things are positive and when these things are negative. And that means that we are going to have to think about the inverses of these functions. When are the inverses actually defined? So when can I just say, for example, if I look at my tan up here, when can I just write this? Theta is equal to tan inverse of x over a in order to recover this thing. We need it to be 1-to-1. Well, we can remind ourselves what the domain of some of these inverses are. And so we could say that for the substitution, x is equal to a tan theta. This requires that theta is equal to tan inverse of x over a, so just what I said. But in this case, that means that theta has to be between minus pi over 2 and pi over 2. Similarly, if you have the substitution a sine theta, this requires that theta is equal to, so just inverting on both sides, sorry, sine, S-I-N. So mostly what I'm doing here is I'm trying to remind you of some of the domains. So in this case, we have, again, minus pi over 2 is less than theta, which is less than pi over 2. And finally, for the secant of theta, this requires that theta is equal to secant inverse of x over a with, and in this case, it's a little hairier. It's much uglier if you remember, or if you look up what the inverse of secant looks like. It has two disconnected components. So one of them will be when theta is between 0 and pi over 2. And this is when x over a is bigger than 1. Or sorry, bigger than or equal to 1. And the other one is when pi over 2 is less than theta, which is less than or equal to pi. And this is if x over a is less than or equal to minus 1. So in this case, it's a much more complicated task. But if you think about the triangles that we were working with, we were primarily concerned. So if I go back and look at this, I'm looking at angles, in this case, between 0 and pi over 2, 0 and 90. So if you look at my little picture, this is an acute angle. It's between 0 and pi over 2. So we're going to do our best, and we will restrict ourselves to the cases when x over a is bigger than or equal to 1. And that means that we can restrict ourselves. Maybe if I put this in a different color just to circle it, we're going to restrict ourselves to that case right there as much as possible. Okay, so maybe you're feeling a little overwhelmed just by seeing this. And of course, mathematics is nothing without seeing examples a lot of the time. So of course, what we're going to spend the rest of the class or this lecture doing is going over examples. You can see this in action because, me writing this right here for you is just compounding confusion. And so once you can see it in practice, that should sort of clear up some of the issues that we might have. So let me show you the first example here of this in motion. So example 1, suppose we're given the integral of 1 over the square root of 4 plus x squared. Okay, so I want to put a little note here. Remember, we were talking about a squared plus x squared. So in this case, a squared is equal to 4. And we're going to take a to be positive. So this will give us a is equal to 2. We don't want a to be negative because it's going to throw off a lot of these inverse relationships here. So, and also it just doesn't matter. So why make your life complicated, right? These trigonometric identities here, and this SOHCAHTOA is always sort of assuming a is positive because we don't have a negative length on the side of a triangle. So we're always going to take a to be positive here, and we always have the ability to do that because we're always dealing with a squared in terms of the integral. Okay, so this is an a squared plus x squared. So that means that we're gonna do a substitution for tangent. So just like that first example I showed you. So let's say x is equal to a2 times tan theta. And this gives me that dx is equal to 2 secant squared of theta. And also a squared plus x squared, as we've already seen with our manipulations here, becomes a squared secant squared of theta, which is equal to 4 secant squared theta. Okay, so then what will we do here? Well, we can start with our substitutions. I'm sorry, I forgot a d theta. So there's a d theta for us on the end. Now this tells us that dx is equal to 2 secant squared theta d theta. So the numerator here becomes 2 secant squared theta. I'll post the d theta on the back here since we have a proper numerator. And my square root becomes 4 secant squared theta. So now I can take the square root here. I'm going to get the square root of 4, which is 2. So that will cancel with the 2 on the top. So let me do that right away. And I get a secant squared theta divided by an absolute value of secant theta. And so I suspect that a lot of people will forget that absolute value. Luckily, we can do that because we are going to assume that theta is between minus pi over 2 and pi over 2, right? So again, if we want to use these trigonometry type results, then this is perfectly fine, right? Theta is our variable. We introduced it ourselves. So we know, maybe I'll put a note in red down here. So for say minus pi over 2 less than theta, which is less than pi over 2. So in these right angle regions, we have secant of theta is greater than 0. And so we need to tell ourselves that's where we're going to restrict ourselves to. And then by telling ourselves that, now we've got a positive thing on the bottom. We're taking an absolute value of it. That's fine. The absolute value does nothing here. So we've got secant squared effectively divided by secant. So now we just get an integral of secant of theta d theta. And now we're in a relatively easy integration. Think about where we started. We started with something that potentially before watching this video, you would say, I have no idea what to do with that, right? There's no way that I could possibly ever solve this thing, at least with the methods we've been given in class so far. But now you follow my chain of equalities and you go, oh, I can do that. The integral of secant. Yeah, I might have to look it up maybe, but I know that this is something that's very doable and it has an explicit answer. And in fact, it's given by the natural logarithm of the absolute value of secant of theta plus tan of theta. So this is one that might be required to be looked up. It's one that I forget quite a bit. But now we've got the issue of exactly what is secant of theta and tan of theta. So we know that tan of theta is given by x over 2, but we need to find out what secant of theta is. So let's draw our little triangle. Let's put our triangle in green here. So here's our triangle. This is my theta right here. It's between 0 and pi over 2. And since x is equal to 2 tan theta, that's the same as having tan theta is equal to x over 2. So I get x, I get 2 here, just like the triangle that I just drew on the previous slide. And from the Pythagorean theorem, I get 4 plus x squared, all under the square root here. So this tells me that cos of theta is equal to adjacent over hypotenuse. So 2 over the square root of 4 plus x squared, just like I said in the theoretical discussion at the beginning here. And this tells me that secant of theta, secant, is equal to, let's make that, we're going to invert that fraction. To make it look a little prettier, let's write it as 1/2 of the square root of 4 plus x squared. But now we've got all that we need to do the back substitution. I can put everything that was in terms of theta entirely in terms of x. So this leaves me with the absolute value of 1/2 4 plus x squared, and then plus x over 2, because that's what tan theta is equal to, and plus c. So you can see when you're performing these, the actual integration doesn't take up that much room. It's a relatively quick process. What takes up a lot of room is your sort of side work, your substitution. You're determining, you're going to have to write down a triangle. Then we might have to refresh our memory on some serious trigonometry here. But nonetheless, it's not that difficult of a process, I think, as long as we can refresh our memory efficiently with some of this trigonometry. Okay, so this example that I just gave is a subset of one that we already have seen. So, for example, for general A, we actually know that sinh inverse, so remember our hyperbolic function, we know that if you take the derivative of sinh of x over a, this thing is actually equal to 1 over the square root of a squared plus x squared. So you might have to go back and reference some of the hyperbolic trig that we talked about previously, but this is something that we know. Now, if you think about what we did with hyperbolic trig, I introduced the hyperbolic trigonometric functions, the usual ones, sinh, cosh, tanch, and then they're the relatives, the cosecant, secant relatives. And I gave them to you as explicit functions. I said sinh is e to the x minus e to the minus x divided by 2. It's an explicit function. I can write it down, right? We just use sinh as a placeholder for that function. Now, the one thing I didn't do, though, is I did not tell you what the inverse functions look like. So now what we can do is we can use trigonometric substitution here to solve the integral on the right-hand side and get an equality for this this trigonometric integral right here, or for for this representation of the inverse of the sinh function. So let's go ahead and do that, right? This is basically the same process as what we just did above. It's actually identical to what we just did above. So I will skip the steps. It's just with general A. We used A is equal to 2 in the previous example, but we saw that this is essentially just equal to the integral of secant of theta. Again, the same thing we just did above, which is equal to the natural logarithm of secant of theta plus tan of theta. So I'm basically just rewriting what I had above. And in this case, we do exactly the same substitution, again, just using general A instead of A is equal to 2. So this gives me 1 over A square root of A squared plus X squared, and then plus X over A plus C. So what this tells me is that the derivative, or sorry, the antiderivative of the function 1 over the square root of A squared plus X squared differs by a constant from sinh inverse of X over A. So we can ask ourselves maybe, what is C? If sinh inverse of X over A is actually equal to this thing, right? Because what we have with that inequality is slightly inappropriate if you really put a lot of thought into what I have written above. Technically, I should not have written this here. I just wanted you to see it. Because remember, definite integrals give you a set. They don't give you one function. They give you infinitely many functions, one for every value of C, all possible antiderivatives. So you can imagine you have this tuning knob, which is the value of C here. And you are saying, okay, what is the value of C that actually makes this the exact antiderivative? This is all possible antiderivatives of that thing. So which one is it that gives me sinh inverse? Well, in this case, we can just pick a value of X and we can ask ourselves what value, for that value of X, what gives us equality here? Because if it works for one value, it works for all of them. That's how this equality is or what this equality of functions is telling us. So let's set X equal to 0. And sinh inverse of 0 is equal to 0. So I get 0 on the left-hand side. And I get the natural logarithm, in this case, of 1 over A times the square root of A squared. So that's 1. And then plus 0, X over A, where X is equal to 0, plus C. So ln of 1, this is equal to 0. So maybe let's put so ln of 1 is equal to 0. You might have to look up some properties of the natural logarithm to remember this, but I can assure you this is the case. And so this tells me that C is equal to 0, and therefore we have an explicit representation of the hyperbolic trigonometric function inverse of sinh. And this is given by just a natural logarithm. So I think this is quite interesting. I think this is really actually a cool property because now we have an explicit expression. If you remember, if you go back to the inverse hyperbolic functions that I gave you, some of it kind of felt like magic, right? I said, okay, well, we can sketch them and we give them this name and let me tell you some properties of them. But it's hard to figure out where some of these properties came from because we didn't have an explicit representation of the function. Now we've got an explicit representation. And if you want, you can pause the video right now and you can go back and look at some of the other derivatives of those hyperbolic trigonometric inverses of hyperbolic trigonometric functions and try and do the same thing. Find explicit representations. Maybe start with cosine inverse. Do the same process. Okay, but I don't want to focus on those too much. I want to just talk about the general method of this trigonometric substitution. We've basically done two examples that are essentially just one. They're the exact same. It's just this one had a cool consequence that I wanted to show off a little bit. So let me illustrate with another one. It's going to be slightly unique here. So let's say now we're given x squared over the square root of 9 minus x squared. Okay, so in this case, we can make a little note for ourselves. I like to do these scribbles in the margins. So a squared is equal to 9 in this case. And this tells me, again, I'm going to keep it positive. So a is equal to 3. Similarly, if I go back a few slides here, I saw that when I have a integral involving the square root of a squared minus x squared, I should be substituting for a times sine of theta. And that's going to reduce me to a square root of a squared times cos squared. Okay, so then let me show you. Let's substitute. So let x equal to 3 sine of theta. So a is equal to 3, so a sine theta. And this gives me dx is equal to 3 cos of theta. And we are going to restrict, again, theta is my variable. I made it up. I get to tell you what happens here. So I'm going to restrict theta to be between minus pi over 2 and pi over 2 in this case. And we should recall that 9 minus x squared becomes 3 cos, becomes 9 cos squared theta. And that's just from a squared cos squared theta. So that's just from the Pythagorean identity, doing a little bit of substitution in there. So what do I get? Well, I have a substitution for x, which is 3 sine theta. So the x squared on the top of this integral becomes 9 sine squared of theta. That's x squared. Then I always forget the d theta on the end of this. D theta, sorry. The dx gets replaced with 3 cos theta. And on the bottom, I've got the square root of 9 cos squared theta, which is just the absolute value of 9 cos of theta. And in our case, because we've restricted ourselves to minus pi over 2 to pi over 2, cos of theta is positive here. So maybe, we have all of these little scribbles in the margins that help us. But this tells me that cos of theta is positive. So that absolute value is completely redundant for me. And again, if you're probably doing this for the first time, you've probably forgot it anyways. So it's okay, right? In this case, it doesn't make a difference. But this tells me that the 3 cos theta on the top and bottom completely annihilate each other. This leaves me with the integral of 9 sine squared theta d theta. Now we've got a power of a trigonometric function, a power of sine. And so if you think about what we did in the previous video, we showed you how to handle this. This was done using a trigonometric identity. You can turn this into a single cosine function by doubling the angle. So if you remember, this will give me, I substitute sine squared of theta for 1 minus cos of 2 theta divided by 2. So you might have to go back and reference the previous video to get this down. But in this case, this is very, very manageable. We can do this, right? Because this will give me, let's pull the over 2 out front. The integral of 1 with respect to theta gives me just theta here. And integrating up that cos of 2 theta gives me 1/2 sine of 2 theta plus c. Okay, so let me scribble something in the margin here again, because we know that we're going to eventually need to do some back substitution. So we've got our triangle, and we use this to determine what theta is equal to. So remember, sine is equal to opposite over hypotenuse. So this gives me x as the opposite and 3 as the hypotenuse. And this tells me down here, again, using the Pythagorean theorem, I get 9 minus x squared for the adjacent. Now, here's a problem, right? We can see an issue has arisen. And that issue is that I don't have a way of finding out what sine of 2 theta is explicitly from this triangle, right? I don't know what happens if I double up the angles here. It's not as simple as just doubling every side of the triangle. Things are going to get messy. So I can pull out my handy trig identities again. So I can replace sine of 2 theta with 2 sine theta cos theta. Now the 2 is going to cancel with the 1/2 here. And so I'm really left with sine theta cos theta. And this is great, right? Because now I'm back down to the regular angle. It's not doubled anymore. So I can do this. This isn't bad at all. In fact, I already know that sine of theta is equal to x over 3. So let's scribble that in the margin too. And from the triangle, I can use SOHCAHTOA again to get that cosine in this case is adjacent. So 9 minus x squared divided by the hypotenuse, which is equal to 3. Okay, so that covers sine theta and cos theta in here. Now we've got a really ugly term. We've just got a theta. That's not coming from the triangle, right? But from our restriction here that theta is between minus pi over 2 and pi over 2, we can invert the sine function. So we can actually say that theta is equal to sine inverse of x over 3. So this gives me 9 over 2. That's still floating out front. Theta is equal to sine inverse of x over 3. That's coming from the fact that x is equal to 3 sine theta. Just isolate for theta. The same way you would do it if you punched it into your calculator to figure out what the angle should be. And then minus x over 3 for sine theta. And then times 9 minus x squared over 3 for cos theta plus c. And if you want to make this fancy, if you want to make it look a little nicer, we can expand out the constants here. In fact, you're going to get a 9 and then divided by 9. So the only constant left in front of this is an x, or is a 1/2, and you get this. So it's not bad, right? But it's hard to get your head around. You should not discount that this is a challenging thing to be confronted with. And that comes from the fact that there's a lot of heavy machinery that's being used to do this, right? The first one is just recalling a lot of basic trigonometry, which I know is not necessarily an easy thing to do, especially if you haven't used it in a while. But then, there's a lot of little tricks involving trigonometric identities that come up over and over and over again, right? So the Pythagorean one is, in my opinion, hard to forget a lot of the time. But some of the double angle formulas are not obvious. They require me to look them up a lot of the time if I need to use them. But the good thing is that, if you do enough examples with this stuff, you start to recognize patterns. You start to say, okay, I should be looking for, a double angle trigonometric identity, or I should be looking for something that gets rid of sine squared, turns it into just cos of 2 theta function. So we have to be careful with this, but the nice aspect of this is that a lot of it is very procedural. As you start going through, you start recognizing that it's the same steps over and over and over again, even though there's a lot of steps that need to be undertaken to go through this. Okay, so let me show you one more example here. And in this case, let me give you this integral. So I'm going to make it a little harder. Dx over the square root of, say, 25x squared minus 4. And I'm going to say, of course, we want to restrict ourselves to where this thing is positive. So we want x is larger than 2/5. So that's one of the two regions, right? It could be smaller than minus 2/5 as well. But we're going to say, assume x is bigger than 2/5. Okay, so the first thing that you're going to say to me is you're going to say, well, I can't do this one, right? Because this one is not in the same form as the ones that you told me originally. You said, I should be looking for something that looks like maybe x squared minus a squared. That's okay, right? We're good at math, right? We're particularly probably pretty good at arithmetic. So we can satisfy, or we can simplify the radical first. So let's say, let the margin scribbling begin. So we have 25x squared minus 4. What I could do is I could factor a 25 out of this, and I get x squared minus 4 over 25. And this is the same as if I pull the 25 out, it becomes a 5 after taking a square root. And here, now I get x squared minus, I'm going to write 4 over 25 as a square, so you can see what the value of a is. This gives me 2 over 5 squared. And so trying to keep with my color scheme I've been using, this gives me a is equal to 2 over 5. And now we're okay, right? Because the 5 doesn't do much. Let me show you what this does to the integral. The 1 over 5 comes out. And now we're in a position where, maybe if we'll write it as 2 over 5 squared. We're in a position now where we can do some trigonometric substitution. And if you allow me to scroll back for a moment, we can see that we're in the case of x squared minus a squared, and we were told that we should be substituting x is equal to a times secant of theta. So let's take a look at what happens. Let's do that substitution. Sorry. Keeping with my color scheme, let's let x is equal to 2/5 secant of theta. So a secant theta. Then dx is equal to 2/5. And in this case, the derivative of secant is secant times tan. So secant of theta, tan of theta, d theta. I didn't forget it this time. And we're going to restrict theta to be between 0 and pi over 2. So everything is positive. We don't really have to worry about simplifying those radicals, because in this region, the tangent function is going to be positive. So let me show you what happens. Here now we get a big chain of substitutions. So the 1/5, that's still sitting out front. Dx becomes 2/5 secant of theta, tan theta. And I like to put my d theta off the quotient in cases where I actually have a numerator that's not 1. And on the bottom here, I get, so if we scroll back, I said that if you introduce this substitution, you can use that secant tan trigonometric identity, and this becomes the square root of a squared tan squared theta, which in our case, tan is going to be positive, so the absolute value is not going to matter. I'm going to jump right over that step, and I imagine that's probably what you're going to do anyways when you're doing some exercises. So let me jump right over it, and this leaves me with a nice 2 over 5 after taking the square root of a squared, and then tan theta. And now we can see there's like a nice chain of cancellations. We might as well just play tic-tac-toe here for a second, and we can knock them all off, and we get a nice integral of secant of theta again. And so we've done this one. We've actually done it twice today. And this leaves me with the natural logarithm of secant of theta plus tan of theta plus c. And the final piece of this is sketching out our little triangle. So let's take a look at what we should have. So continuing with the margin sketching. It doesn't really matter what the proportions of your triangle are. I sort of draw the same triangle every single time. The point is just to visualize it, right? So if you want, you can try and draw it to scale, but it doesn't really matter. So here I get 25x squared minus 4. And in this case, I get 5x. So this is just coming from the case that I have x is equal to 2 over 5 secant of theta. That means that secant of theta is equal to 5x. That's my hypotenuse. And divided by 2, that's my adjacent. And then I just use the Pythagorean theorem in order to simplify this, right? So this is 5x squared, that's 25x squared, minus 2 squared, which is 4. And so in this case, I am going to get, I already have what secant of theta is. And so the only thing left is to figure out what tan of theta is. So tan of theta, this is going to be opposite over adjacent. So it is 25x squared minus 4 divided by 2. And so now we can just fill in everything that we know doing our back substitutions. We got 1 over 5 times the natural logarithm. We said that secant is 5x over 2. That is just taking this piece right here and rearranging for secant of theta. Then plus, we just calculated that tan is 25x squared plus 4, minus 4, divided by 2 plus c. It's not going to get much prettier than that. I'm not even going to bother trying to simplify it more because it's, it might even just make it look worse. Okay, so what have we seen today? We've seen that we can take integrals in terms of x that don't involve any sort of trigonometric functions, and we can do a substitution where we artificially put a trigonometric function into it. Now, the first time you hear this idea, you probably think it's ludicrous because polynomials or things with powers of x's, in my mind at least, are typically easier or just easier to think about than trigonometric functions. But based on the work in the previous video, and now based on the work today, we've seen that actually this can greatly simplify the process, and it can leave us with much simpler integrals. But the difference now is that the process becomes slightly more involved, right? There's a lot more steps that need to be taken care of, especially, the substitution needs to be done correctly. And then the undoing of that substitution requires us to remember a lot about trigonometry, which could be, lost to the recesses of time at this point. We might have to relearn a lot of our basic trigonometry, our SOHCAHTOA, if you're familiar with that term. But, getting over that hump, life is pretty good. Most of the work or most of the integrals that you're going to see are very, very similar to these examples that I've shown you. So this should give you a nice base from which you can sort of launch off of and continue to work with more difficult integrals going forward using this method of trigonometric substitution.